Now let's take a look at the Timoshenko beam element. And I will be using again the general displacement interpolation to formulate that element. So let's say element with general displacement interpolation. So the main difference of this element from the Bernoulli-Euler beam is shear deformations are considered. So we are not ignoring them, we are considering their effects. That's the main difference. The rest of the assumptions are the same. So let's take a look at the shear deformations again. And I will calculate the internal energy due to the shear deformations. So again, I'll start with this cantilever beam. And from this distance x, I'm taking an infinitesimal element whose length is dx, and the length of that cantilever is L. And if you remember, let's take this infinitesimal element here. So that's our, I'll just draw the undeformed status here. This length is dx, and according to our definition, the angle change from 90 degrees is defined as our shear deformation. That's the shear deformation. So and we said that the shear deformation is caused by the shear force. So I can write the internal strain energy due to shear deformation as follows: from 0 to L, 1/2 times force times corresponding deformation integrated over the length of the member. So let's call this equation 1, and that's the internal strain energy due to shear deformation. Now recall that shear stress is equal to shear force divided by the shear area, and from that equation I'll obtain shear force as equal to shear stress multiplied by the effective shear area. Let's call this one as equation star. So inserting star into equation 1, we get the following expression: UE is equal to, from 0 to L, 1/2 shear stress multiplied by the effective shear area multiplied by the shear strain times dx. And also recall that shear stress is equal to shear modulus times shear strain. So now I'll call this equation as plus, this equation as plus plus. Now again, inserting equation double plus into plus, we get our expression, the equation for the internal strain energy due to shear deformation, which is equal to 1/2 times shear stress multiplied by shear modulus times effective shear area multiplied by the shear strain and integrated over the length of the member. So that's the internal energy for shear deformations. So we can write the following equation. Thus, for a beam element with shear deformations, total strain energy is as follows. So internal strain energy is equal to, from 0 to L, 1 over 2 curvature multiplied by EI multiplied by curvature dx. Remember that that's the strain energy due to bending deformation, plus from 0 to L 1 over 2 shear strain multiplied by shear modulus times effective shear area multiplied by shear strain dx, and that's the strain energy due to shear deformation. So basically, this first part of the equation describes the energy due to the following shape change. Remember that this is our infinitesimal element, and due to the bending deformation, we see a deformation as follows: squares into trapezoids. That's the definition of the bending deformation. And in the second case, again we have an undeformed squares. This infinitesimal square becomes a parallelogram, and that's the definition of the shear deformation, and this equation is the energy due to the following deformation in the member. So basically we separated these two deformations. We are just assuming that they are they don't influence each other. So bending deformation causes squares to become trapezoids, and that's the energy equation of it. And shear deformation causes squares into parallelograms, and that's the energy of it. Now we are ready to formulate the element. So I'll call it Timoshenko beam element. So let's again define our element. So that's x-axis and deformation u. That's our y-axis, and the deformation is v. And this is the neutral axis of the element. So let's show a deformed shape. Let's say that the element deforms in the following manner. So that's again the neutral axis of the element, and this displacement is v of x. Now the difference here is the plane sections doesn't remain plane, but they don't have to be perpendicular to the neutral axis. So I can have, let's exaggerate it a little bit. A deformed shape as follows. Sorry for the bad drawing. Let me redraw it. Okay. Now let's take an infinitesimal element somewhere here, and let's show it in the deformed configuration. So let me put this coordinate axis here also. That's x, that's y. Now the derivative of this element at this point, let me use a different color now, is this one. So this angle is dv over dx, but we have also a shear deformation, so let's show that also. In addition to that, I see some shear deformation here, so it increases the angle, and that deformation is our shear strain. And this total angle, the total angle change will be theta. So that's the definition of the Timoshenko beam element. We have a first order correction for the shear deformation. In other words, I assume, now that's dv or dx, that's the angle. If we don't have any shear deformation, this is what we see. This is what we assumed in Bernoulli Euler beam. The rotation is equal to dv over dx, okay? Now in the Timoshenko beam, we say that the shear deformation will be linear with respect to the depth of the member. So this, we have some additional deformation due to shear. That deformation causes only angle change, and the amount of the angle change is defined as the shear strain in this infinitesimal element. So my total rotation is dv over dx due to the bending deformation plus gamma due to the shear deformation. So I can rewrite my rotation information as follows. We have theta is equal to dv over dx plus shear deformation. Okay, let's call it equation star. So basically what we do in this Timoshenko beam element is we add an additional deformation to the rotations. Now we know that the shear strain is equal to shear divided by G times AS. And from the strength of materials, we know that the shear force is equal to EI times the third derivative of the transverse displacement. So combining these two equations, I can write the shear strain as equal to EI g time divided by g times as multiplied by the third derivative of the transverse displacements. Now, also recall that we have the following parasitic shear definition that we use in the shear derivation of the beam element with shear deformations. That's equal to 12 EI divided by G times AS times L squared. This is called parasitic shear deformation, or basically shear slenderness. If this value is large, then you will observe more shear deformation in your structure. Okay, the reason of using that parameter is if you go take a look at your nodes or the derivations of the beam element with the shear deformations, they are all represented in terms of parasitic shear deformation or shear slenderness, and I will use the same approach. So if I write the shear strain in terms of the shear slenderness term, then the shear strain becomes equal to L squared divided by 12 multiplied by the shear slenderness times the third derivative of the shear deformations. Right? Now, we said that I will do the formulation of this element using the Legendre polynomials. So, if we use general displacement field with Legendre polynomials, then the third derivative of the transverse displacement becomes equal to 120 divided by L cubed multiplied by D4. Okay, so my shear strain will be equal to 10 over L multiplied by the shear slenderness times D4. So what we observe here is when I assume a general displacement field or the cubic deformed shape, the shear strain depends on only D4. Remember that D4 describes the anti-symmetric bending. So we have shear strain due to anti-symmetric bending only. So the rigid body translations, rotations, and the symmetrical bending doesn't cause any shear deformation. It's only caused by the anti-symmetric bending mode. That's what we see from this equation. All right, so let's continue. Now recall that for the Euler beam, Bernoulli Euler beam, the rotation is defined as follows. It's just dv psi divided by d psi, and that's equal to L1 prime d1 plus L2 prime d2 plus L3 prime d3 and L4 prime d4. Now redefining the rotation interpolation, let's say, using equation star. So we are using this equation, that equation. So dv over dx interpolation is as follows. The shear is equal to this one. We just add them up. In that case, my rotation interpolation becomes equal to L1 prime d1 plus L2 prime d2, L3 prime d3, L4 prime d4 plus shear slenderness 10 over L multiplied by d4, and that's my rotation interpolation. So by using that interpolation, let's take a look at the displacement transformation matrix, or G. So for Timoshenko beam element, the displacement transformation matrix so G is equal to, this part doesn't change because the displacement interpolation is the same. So this part I have 0, 2 over L minus 6 over L. This part is different. We have 12 plus 10 times shear slenderness over L. The third row doesn't change. It relates to, again, the transverse displacements. And I have 0, 2 over L, 6 over L, and again 12 plus 10 phi divided by L. So I have my G matrix is different, and by using that G matrix I can calculate the H matrix as the inverse of G. Now let's take a look at how we calculate the stiffness matrix. So I'm taking a look at the internal strain energy, 1 over 2 from 0 to L, curvature multiplied by EI times curvature dx plus from 0 to L the shear strain multiplied by G times AS times shear strain times dx. Okay. Now we said that in the previous case K is equal to L double dot, right, multiplied by the D. L double dot is the second derivative of the Legendre polynomials. And remember that, let's do the curvature interpolation. We say that curvature is equal to d theta over dx, and for the d theta we can again use the following equation, and that's equal to d square v over dx squared plus d shear strain divided by dx. And when we use the Legendre polynomials for the shear strain, you see it's constant, so its derivative with respect to x is equal to 0. This is for interpolation with Legendre polynomials. So this part of the equation, or this part, remains the same. It doesn't change. It's the same as the Bernoulli Euler beam. So let's take a look at the shear strain interpolation. So we said that the shear strain is equal to, now I'll write it in matrix form. We have 0, 0, and 0. V times 10 over L multiplied by D1, D2, D3, and D4. So if I call this matrix as our B shear matrix, then I can write shear strain is equal to B for shear multiplied by the displacements. And that's the equation for the shear. Okay. Now inserting these two equations into the internal strain energy equation, this is what we will get. The internal energy is equal to 1 over 2 integral from 0 to L d transpose, the second derivative of L multiplied by EI, there's transpose here, second derivative of L times d integrated over the dx, plus from 0 to L dt, the bs transpose multiplied by g times as multiplied by bs multiplied by displacement times dx. So this part, we call it, remember that, KK, stiffness matrix for bending deformation. For general displacements. And this part, I can call it KKS, stiffness for shear deformation. Again, this is for general displacement interpolation. So for the nodal deformation, I can apply the transformation Let's do that from 0 to L. Now I have the nodal U H transpose L double dot multiplied by transpose, EI. Again L double dot multiplied by H times U dx plus, forgot to write 1 over here, 1 over 2 from 0 to L U transpose H transpose BS transpose G times AS times BS times H times U dx. So I will call this part of this expression as KB. This is the bending stiffness. And this part of the equation as KS, which is the shear stiffness. So in much simpler form, UA becomes 1 over 2 from 0 to L U transpose times K bending U times dx plus 1 over 2 U transpose times Ks times U dx. And if we take the first variation, we end up with the following equation from 0 to L KB plus Ks multiplied with U times the variation in U dx. So as you see, the stiffness matrix of our element is nothing but the summation of the bending stiffness and the shear stiffness. How do we calculate the bending stiffness? If you want to calculate it in the general displacement field, this is the equation, and then you can transform it, or you can just directly calculate with this equation. That will give you the bending stiffness. And for the shear stiffness, you can use this equation. Okay, let's take a look at the Timoshenko beam element, the implementation. Again, we will be using the Legendre polynomials, and the first one represents translation, rigid body rotation, symmetrical bending, and anti-symmetrical bending modes, and how much they are effective is determined by these coefficients. Here I call them Q again, but in the derivation we call them D. So the same procedure, I'm just converting them into the Cartesian coordinate system, and this is the displacement interpolation and the rotation interpolation. But of course, this is the rotation interpolation for the Bernoulli-Euler beam, right? We don't have any shear deformation here. So here I'm manually adding the corresponding value. That's our, remember, that's our shear strain, right? In this equation, we are saying that theta is equal to dv over dx plus first order correction to rotation, which is the shear strain. How did we obtain this 10 over L? Remember that we use the third derivative. This is the third derivative of the shear deformation, which is equal to 120 Q over L cube. And remember that we said that shear deformation is equal to L square over 12 parasitic shear multiplied by the third derivative of the transverse deformation. So if you just put this into here, we obtain this value 10 over L Q4. And this total equation is for the rotation interpolation. So when we calculate the nodal displacement and the general displacement relationship, this part is the same because this part of this interpolation has not modified. I only modified the rotation. So these first and the third rows of the G matrix is the same. The second row, so I'm using this operation, putting x equal to 0, gives me the following. Then I put x is equal to L, and I obtain the following equation. So if I represent it in matrix form, that will be our G matrix. But in the transformation, we use the inverse of it. So when I take the inverse of that G matrix, I obtain the following transformation matrix. Now the rest is again similar. Now the general stiffness matrix in the general displacement field, we see that the bending, the curvatures are not influenced by the shear deformations. So we have the same curvature matrix as in the Bernoulli-Euler beam, and that's the equation to obtain the stiffness matrix. Now for the shear deformations, we derive that. So the shear Q1, Q2, Q3 has no effect on the shear deformation, only the anti-symmetric bending mode, and that's the relationship. And in order to calculate this, yes, I have to perform the following calculations. So instead of GAS, I use the following so that I obtain all the equations in terms of EI. Okay, so you just obtain that by using the definition of V and write G times AS in terms of EI. Now the difference here is I show this BS or LT matrix in the vector form, but in the derivation we just show it in the column form. So that's why the transposes change and switch places, but it's the same thing. So anyway, that's the BS matrix. That's the way we calculate the stiffness matrix in terms of the general displacements. So the bending stiffness is the same. That's our bending stiffness coefficients. They are exactly the same as the Bernoulli-Euler beam. But in addition to that, we have an additional stiffness due to the shear deformations. So in our derivation, we saw that the element stiffness matrix is nothing but the summation of these two matrices. So here I sum them up. That's the stiffness matrix in the general coordinate system. So in order to transform this into the nodal deformation, I pre-multiplied it with H transpose, post-multiplied with H, and I obtain again our stiffness matrix with shear deformation. And if you think about it, this is exactly the same matrix that we derive by using the stiffness method.